There was a time when every American garage held a small collection of tools that had nothing to do with cars in the way we think of cars today, and everything to do with the machines that ran underneath the hood, behind the wall, and inside every appliance in the house. He did not learn these tools from a manual either. He learned them from the man down the street who rewound motors on weekends, from the mechanic who had been setting points since before power steering existed, from the uncle who kept a workbench full of tools that hummed with a kind of electrical knowledge nobody bothers to pass down anymore. Most modern men under 40 would not recognize half of what sat in that drawer. Not because electric motors disappeared, they did not, but because the era of fixing them disappeared, replaced by an era of throwing them away. Number 7 is a tool tied to a measurement that almost nobody under 40 has ever even heard of, let alone used with their own hands. Let us get into it. Number 7. Spark plug gapping tools. Every American man who owned a car before the late 1990s owned one of these, usually a small flat disc with graduated slots cut into the edge, sometimes combined with a tiny bending hook on a folding tool that lived in the glove box next to the registration. Spark plugs in those days came out of the box close but not exact, and an engine running smoothly depended on the gap between the center electrode and the side electrode being correct to within a few thousandths of an inch. Too wide, and the spark would struggle to jump the gap, especially in cold weather. Too narrow, and the spark would be weak, fouling the plug over time. A man would pull each plug, slide the correct wire gauge into the gap, feel for a slight drag, and if the drag was wrong, he would hook the side electrode with the bending tool and gently tap it closer or pry it farther, checking again, adjusting again, until the feeler gauge slid through with exactly the right resistance. This was done for every plug, every time, whether the plugs were new or simply pulled for inspection. A man who skipped this step was gambling with a rough idol, and he usually found out the hard way on a cold morning. Modern spark plugs arrive pre-gapped from the factory, built with electrodes designed not to be bent at all, since bending them on some of the newer fine wire designs can crack the porcelain or snap the electrode clean off. The gapping tool still exists in some toolboxes, rattling around at the bottom of a drawer, but the skill behind it, the feel of the feeler gauge sliding through at exactly the right resistance, has nothing left to practice on. Number 6. Distributor machines. Before computers decided exactly when each spark plug fired, that timing was controlled by a spinning mechanical assembly called a distributor. And inside that distributor were small moving parts, weights, springs, and a vacuum diaphragm. That changed the timing slightly depending on engine speed and load. A distributor machine was a benchtop device, often the size of a small washing machine, with a variable speed motor on top that could spin a distributor at different RPM while a vacuum pump simulated the engine's intake vacuum. A mechanic would clamp the distributor onto the machine, spin it up, and watch a strobe light or a dial indicator to see exactly how the timing advanced as the speed increased and how it responded when vacuum was applied or released. If the advance curve did not match the specification for that engine, the mechanic would open the distributor, swap the springs for a stiffer or softer set, or bend the weight stops slightly, then run the test again. This was not guesswork. There were charts, specification sheets for hundreds of distributor part numbers, each one showing exactly how many degrees of advance should occur at exactly how many RPM. A shop that did this work well could make a tired old engine run smoother and more efficiently than one fresh from the factory, with a poorly matched distributor. The distributor machine itself became obsolete almost overnight once electronic ignition and then computer-controlled timing arrived, because there was simply nothing mechanical left to test. The machines themselves now sit in the back corners of old shops, unplugged, taking up space, a benchtop reminder of an entire branch of automotive knowledge that simply stopped being needed. Number 5. Dwell meters. If the distributor machine tested the mechanical heart of the ignition system, the dwell meter tested its electrical heart. Inside the distributor sat a set of contact points, two small metal surfaces that opened and closed thousands of times per minute, controlling exactly when the ignition coil released its charge to the spark plugs. The dwell angle was the number of degrees of distributor rotation during which those points stayed closed, and that angle determined how much time the coil had to build up its charge before the next spark. Too much dwell and the points would burn out quickly from excessive current. Too little dwell and the coil would not have enough time to charge fully, producing a weak spark at higher engine speeds. A dwell meter was a simple dial gauge calibrated in degrees that clipped onto the ignition circuit and gave a direct readout while the engine idled. A man would pull the distributor cap, loosen a small screw holding the points in place, and with the engine running, slide a thin screwdriver into a slot to shift the points closer together or farther apart while watching the dwell meter needle, adjusting in tiny increments until the needle sat exactly where the specification called for, usually somewhere around 30 degrees, depending on the engine. This was routine maintenance, done every few thousand miles alongside an oil change, because points wore down from the constant arcing and the dwell angle would drift over time. Electronic ignition eliminated the points entirely sometime in the 1970s and 80s, and with them went the need for a tool whose entire purpose was to measure something that no longer existed in the engine at all. The dwell meter still works perfectly. There is simply nothing left for it to measure. Number 4. The insulation guillotine. Step away from the car now and into the motor shop, where men rebuilt the electric motors that ran washing machines, furnace blowers, factory equipment, and the starter motors in those same cars we have been discussing. Every electric motor has slots cut into its iron core, and every one of those slots needs to be lined with insulating paper before the copper windings go in. Paper thin enough to fit in a tight slot, but tough enough to survive decades of heat and vibration, without breaking down and allowing the windings to short against the iron. This insulating material, often called slot paper or fish paper depending on its composition, had to be cut to an exact width and length for each motor, because a piece even a 1/16 of an inch too wide would not seat properly in the slot, and a piece too short would leave copper exposed at the ends where it could arc against the frame. The insulation guillotine was a long, narrow cutting tool, essentially a fixed blade mounted on a hinge above a flat bed with adjustable guides that let a man set a width, slide a large sheet of insulating material under the blade, and bring the handle down in one clean stroke to produce a perfectly straight cut every time. A shop rewinding several motors a week might cut hundreds of these pieces, and the guillotine made each one identical to the last, which mattered enormously when a motor needed dozens of slots all lined the same way. Without a guillotine, a man cutting this material with scissors would produce slightly different widths every time, and slightly different widths meant some slots fit loose and some fit tight, and a loose fit in even one slot was where a future failure would start. Number 3. Wedge inserting tools and slot scrapers. Once the old windings were pulled out of a burned-out motor, and they often came out in a tangled, melted, blackened mess after years of running hot. What remained behind in each slot was a residue of old varnish, carbonized insulation, and sometimes rust or corrosion baked onto the iron itself. Before any new wire could go in, every one of those slots had to be scraped completely clean, because any leftover debris could create a rough spot that would cut into the new wire's insulation as it was wound through, creating exactly the kind of short circuit the rebuild was meant to fix. Slot scrapers were thin, flat tools with hooked or angled tips, shaped specifically to fit into the narrow channels of a motor core and drag old material out without gouging the iron itself, since a gouge in the iron could create its own sharp edge that would cut new wire just as easily as old debris would. Once the slots were clean and the new insulating paper was in place, and the new copper windings were threaded through, wedge inserting tools came into play. These were long, narrow, often wooden or fiber tools, shaped almost like oversized tongue depressors with a slight curve. used to push thin insulating wedges down into the open top of each slot, locking the windings in place against the force they would experience once the motor spun up to speed. A man had to seat each wedge firmly enough to hold the windings tight for years of vibration, but gently enough that he did not crack the wedge or nick the insulation on the wire just below it. This was done slot by slot, sometimes dozens of times per motor by feel, with a rhythm that an experienced rewinder developed over years and could repeat without looking. His hands knowing the depth of a properly seated wedge, the way a carpenter's hands know the depth of a properly driven nail. Number 2. Taping needles and winding pliers. Inside a motor, the copper windings do not simply sit loose in their slots. The ends of the windings where one coil connects to the next have to be bent into shape, routed around the core in specific patterns, and then tied down tightly so that when the motor spins at full speed, centrifugal force does not fling those connections loose and tear the whole winding apart. Winding pliers were specially shaped, often with curved or offset jaws, designed to grip and bend heavy-gauge copper wire into tight, consistent shapes without nicking the enamel insulation that coated each strand, since even a small nick in that enamel coating could allow two windings to touch and short against each other. Taping needles were long, curved needles, sometimes a foot or more in length, used to pass cord or tape underneath and around bundles of windings in places where a man's fingers simply could not reach, lacing the windings together the way a shoemaker laces a boot. Except the stitches here had to survive heat, vibration, and decades of continuous operation. A skilled motor rebuilder could lace an entire rotor's worth of windings with these needles in a pattern that looked almost decorative, tight crossing loops that held everything immovably in place. And he did this from memory because every motor size and winding pattern had its own lacing diagram that an experienced man simply carried in his hands. Number 1. The commutator undercutter. This is the tool that contained all the others, the one that determined whether every hour spent rewinding a motor would be wasted or worthwhile. On a DC motor, the commutator is a cylindrical ring made up of dozens of individual copper segments, each one connected to a different part of the winding, with the carbon brushes riding across the surface as the motor spins, transferring current into and out of the rotating windings. Between each copper segment sits a thin strip of mica, an insulating mineral that keeps the segments electrically separate from each other. Copper wears down slightly over time from the brushes riding across it, but mica does not wear at the same rate, and if nothing is done, the mica eventually stands slightly higher than the surrounding copper, creating tiny ridges that catch the brushes, cause arcing, throw sparks, and chew through brushes at an alarming rate. The commutator undercutter was a small tool, sometimes hand-operated and sometimes powered by a tiny motor of its own, fitted with a thin blade or grinding wheel exactly the width of the mica strips, that a man would draw carefully along each gap between segments, cutting the mica down slightly below the level of the copper, restoring that smooth, even surface the brushes needed to ride across without sparking. This had to be done on every single gap around the entire commutator, dozens of times per motor, with absolutely consistent depth, because one gap left too high would create exactly the arcing problem the whole job was meant to eliminate, and one gap cut too deep would weaken the segment and shorten the commutator's life. A motor rebuilt perfectly in every other way, with flawless windings, clean slots, and tight wedges, would still arc and fail prematurely if the commutator had not been undercut properly, which is why an experienced man always did this step first, checking it, rechecking it, and only then moving on to everything else. Notice what runs through every tool on this list. None of them were exotic. None of them required a factory or a fortune. Just a workbench, steady hands, and someone willing to show a younger man exactly how deep was too deep and exactly how tight was too tight. That feel, built slowly over thousands of motors and thousands of distributors, is what disappeared from American garages, not the machines themselves. Electric motors still wear out, Old engines with points and distributors still exist, parked in barns and driveways, waiting for someone who remembers what a dwell angle even is. The tools themselves are often cheap, sitting in bins at swap meets for a few dollars each, unwanted, unrecognized, waiting for a man willing to pick one up, turn it over in his hands, and learn what it once meant to keep something running instead of replacing it.